chair for this session, Elizabeth Boschee. She's a research team leader at the USC Information Sciences Institute and the director of the ISI Boston office. Liz?
Hi, everyone. It's great to see you, or to see you remotely today. We're going to be talking today about language diversity. Language is critical to human experience, so it's critical to AI, and there's a lot of really interesting things going on there. So without further ado, I will start the first presentation. If you have questions, please feel free to type them into the Q&A box, and we will have some time for questions at the end of all 5 talks. So starting off, Dr. Jonathan May is a research assistant professor in the computer science department at USC and a research lead at ISI. His research interests include machine translation, multilinguality, generation, semantics, and low resource learning. Take it away, John.
Hi, everybody. Thanks, Liz. So if we go on to the first slide, today I'm going to talk about automatic translation, or we call it machine translation. And start off by saying that one problem that we have today is that, so if we look at the graph on the right, the yellow circle at the top shows all of the languages that are not covered by machine translation. And you can see there's a tiny little sliver that is not in that yellow ring that are. But this is a major progress because this actually accounts for 108 languages that Google provides machine translation capability for as a way of measuring. And while that seems like a small number, if we look at the bottom graph, there we are looking at speakers of languages in the world. And now the yellow shows that about 20% of speakers are represent this 98.6% of the world's languages. So the 108 languages that we can translate covers 80% of the planet, but 20% of the planet is still 1.5 billion people. And for these people, they speak 98.6% of the world's 7,000 odd languages. And so there's just a tiny amount of data available, if any, for being able to construct translation for these models. And this is important because if you can't translate and can't understand somebody's language, then there's a limit to the amount of international cooperation that can occur. And so, for example, if an organization like USAID wants to provide support when there's a sudden crisis in an area where one of these much lower resource languages is spoken, and people are trying to get help using their native language, it can be very difficult to understand what aid needs to be provided. And so this is one of the focus areas that we have addressed. Over the past 4 years, we've been working on a program called Lorelei that builds machine translation when there's a crisis. So given a sudden crisis, you want to stage a system as fast as possible, ideally within 24 hours. And we've been doing this for languages like Uyghur and Tigrinya and Kinyarwanda with good success, oriented towards these topic domains. But sudden crises aren't the only kind of way in which international cooperation could be better. So there's these long-term ongoing crises that we know about and actually can't really do much for. So I'm speaking specifically on this slide about the immigration and asylum crisis at the southern border of the United States currently. We know that there's many thousands of people coming, and there's thousands of people who are trying to get asylum who are fleeing political oppression, sex slavery, and violent intimidation. And their languages are not Spanish or English, but they speak often smaller indigenous languages. And as such, they're having a hard time making an asylum case because even though they've suffered great torments, they're not able to properly prepare with an immigration lawyer ahead of an interview, which determines whether or not they're going to be granted asylum. And it's really important to be able to prepare with these lawyers, but the lawyers generally that are available speak English or sometimes Spanish. So we're building crisis interview translation software for some of these languages like Mixtecs, the Mixtec family of languages, Kanjabal and Quiche. And we're partnering with Questions Ilievski from the School of Social Work to collect interviews so that we can see how well we're doing on this very particular kind of domain. And we're also using techniques about domain shifting that involve data that's not even necessarily in these languages, but is about people testifying or discussing the sorts of horrors that they've had to witness, and that's using USC Shoah Foundation's data. Okay, so that's what we're doing. Now, what are the means in which we're able to build these rapid systems and these far-ranging systems, even though there's not a ton of data? So in some cases, we sort of pivot and try to create data or create solutions where we don't necessarily have your traditional many millions of words of a sentence and its translation. So we build these tools. One of the tools is this universal Romanizer that takes advantage of the Unicode table, which provides support for nearly all of the world's writing systems, and in its metadata has clues that allow us to convert all the writing systems into a common Latin script that is close to being pronounceable. And this allows us to, for example, share information between, say, Uzbek, which is very similar, very related to Uyghur, but the two use completely different writing systems. But if you normalize them into a common space, then you can actually share vocabulary information. And another tool that we use, which we call the Chinese Room, in honor of John Searle's famous thought experiment, lets us be machine translation engines and try to construct high quality, if low yield sentences, so that we can evaluate our machine translation systems by going word for word and using our own intuitions to try to create coherent sentences. And this has been used and ported into other types of natural language processing techniques like information extraction, where we can again annotate for information extraction without knowing the language that we're annotating in. Next slide, please. So turning to the data that we do have, the parallel data that's used to create machine translation systems, we focus on the modern neural machine translation systems that use transformer architecture and are out of the box and not particularly well suited to training if you have a very small amount of data. But we pioneered a method, which is now actually fairly commonplace, of using transfer learning for low resource neural machine translation that trains a model using a data set that's large, but not necessarily related to what you want to ultimately learn how to translate. So we can take a very large French English data set, train a model, and then from that trained model, use that as a starting point to then train with a new language. And we pioneered how to do that for machine translation. And we extended that further. We're saying, well, a French-English machine translation system baseline is fine, but actually if you take a very many different language to English system and Romanize everything using the Romanizer, then you get the sharing of words and you get a much more robust and faster training system. And we've also developed methods of hyperparameter selection. This is very important for transformers in general, and especially low resource transformers, to pick proper hyperparameters. And one that's very important and often overlooked is determining how much to break up your input words. Rather than just say using white space to separate them, you can break them up in the middle somewhere, or you can go all the way to character separation. And figuring out exactly where to do that ends up being a function of the sentence length and vocabulary diversity. And so we've studied ways to pick the right boundary without having to build multiple systems. Next slide. So we put these tools and these models together and have made a nice engineering contribution, which is this 500 language open translation model. This is primarily by my student TG, who has built three components. One is called MT data, and the way that works is you go and you mention the languages that you'd like to translate, and it goes out to the web and to various collections of parallel data and downloads everything that's relevant and builds nice parallel data files that MT practitioners want to use. He's built a lovely memory efficient vocab management system called NL Codec, which handles a lot of this tokenization I talked about and represents things in integer form so that they're useful, kind of some deep internals, and RTG, which is a flexible machine translation model that also can be used very easily in a server mode, and you can stage demos. It has a nice REST API interface with it, and he's used that to build this massive 500 language to English model built with a huge amount of data, and that's a nice starting point to use to then fine tune into the language that you care about. And so that's available for use and download, and yeah. So, and the final thing I want to talk about is getting a little bit looking into the sci-fi future is what happens if you want to do translation and you're not even sure that you've seen this language before. It's maybe some novel language, maybe some alien language. I'm not going to go that far yet, but what we have looked at is this notion of being able to understand what's being said by the just general properties of language. And this finds its approach in decipherment. And so we built an end-to-end decipherment model using these transformer architectures that takes in any kind of encryption of a language, such as this Borg cipher, which comes from the Vatican secret archives from the 17th century, and it's written in an unfamiliar character set. And we can use this model, even though we've never seen Borg cipher data before, it's not trained on that, to generate the Latin underneath it. And that same model will also take, say, some encrypted English and translate that or transform that into its proper English. And we think we can use that, the properties of language in general, to maybe deal with, say, some heptapod if you happen to come upon it. But we're definitely not there yet. So anyway, that concludes my talk today. Thank you very much.
Thank you very much, Jon. All right, so moving on, I believe Marjorie Freedman is next. Marjorie Freedman's research focuses on language understanding and the application of language understanding technology to user applications. In a number of projects, she has explored how integrating information across modalities improves understanding.
Thanks, Liz. So I'm going to talk today about multimedia extraction, really from the perspective of somebody whose background is primarily working on language. And so why multimedia? Well, in general, a lot of my work focuses on building systems, doing research that helps us observe a data stream and then organize that information, or make predictions based on that information, or answer questions based on that information. And these data streams aren't just text. They might have audio, they might have images, they might have text embedded in those images. And there are a number of reasons that you want to pay attention to these other streams. So Jon just talked about doing machine translation, but if you have a caption and an image together, even without that machine translation, you can get a lot of information from the content. Approaches that look at only one modality are going to miss information. And the information itself is often ambiguous. The models that we build are often errorful. They're not perfect. And so multiple sources can provide confirmation, can help improve the overall accuracy of the machine's understanding of the data that it's looking at. So to go into a little bit of detail about missing information, when you look at text and images, one of the things that you see is a difference in granularity in what's reported. And so in work actually with Jon and Ralph and others, we're exploring, can you discover schemas, scripts from large data corpora? And in this example, so recipes are a nice example where scripts are very explicit, where the process is very clear and described. You see this difference in granularity. So in the text, you see that you need to rub oil and sprinkle salt and pepper on the potato. And there's an explanation of why, that it adds flavor and makes the skin crispy. But if you were trying to explain to an agent all of the information involved in this picture, you need a lot more words. And so you're not rubbing the oil with your fingers, you're using a brush. And you see that in the image. When you go to test if the potato is done with that fork, you need to have picked up the fork and hold it. And you're not touching the potato, you're using tongs to hold it still because the potato is probably hot. And so in some contexts, capturing all of that information, much of which is likely never to be written because it's so obvious to all of us, is really important. And that's a place where images can fill in. Second thing that the images can help with is resolving uncertainty and error. And so often the text alone is ambiguous. So this isn't system error. This is just USC being an acronym that refers to many places. And so if we just see this tweet USC to require vaccinations, we don't know if we mean the University of South Carolina, the University of Southern California, or one of the other USCs out there. But if we grab the image associated with that tweet and process it and capture the fact that there's text in it and recognize that text, the disambiguation, knowing which USC we're talking about, is obvious. And that comes to us from the image. And so a challenge associated with this goal, and one of the reasons that I'm not going to go into a lot of detail about how we do all of these things, is that it's a simple goal. We want to understand all of the information, but it ends up being a very complex pipeline. And so a different group of us put together a demo of a system that really does try to take multilingual, multimedia information and organize it into a structured database resource that can be queried and used for downstream analytics. And on the right is a simplified system diagram of all of the things that went into that overall goal. And you'll see even within each of those boxes, you often have several different models. So within visual entity extraction, we have a number of different models feeding in and fusing and improving the system. And within that system diagram, there's information that's missing. So we're missing taking the audio and turning it into going from speech to text, or on my slide here. And we're missing the OCR because we didn't include those in the demo. And we're also missing some important types of information that you might want. So we hadn't incorporated sentiment analysis at this point. We hadn't incorporated understanding the emotion behind the text. So as you try to bring in all of this information, you end up with complex systems pulling things together. Next slide. So another challenge that we face is trying to see, are those hypotheses that I talked about in terms of what you want to get out of the data, are they really present in the data? And so something that I've been spending a lot of time thinking about recently is in the type of data that I'm most often encountering when I read the news, when I work on news corpora. Do the images provide this type of missing information that's useful for a task that I'm interested in, or confirming information that helps disambiguate? And one of the things that I'm finding is that that's not true, which leaves open the question, why are these images here? And so going from the relatively uninteresting, the images required by the format, to a motivation that's still hard to know what to do with, which is the image grabs your attention. It functions a little bit as clickbait. It makes it more pleasant to look at, which is maybe why it's required by the format, to things that I think we could try to capitalize in multimedia information, which is the image provides a really quick summary of what's important. What is the topic of this? And it also frequently evokes some type of emotional response. And it's not always clear that that fits into traditional taxonomies of emotions, but the right two images look like people celebrating. They look like fun. And that's something that the author and publisher wanted you to get out of these images. And so moving on to more thoughts of data, because I've been looking at a lot of multimedia data recently, I've been looking some at infographics and what we would want to do if we were trying to process infographics. And so a lot of the work that I've done with my collaborators has been focusing on images that are more photographic. But especially as you look at social media, you see all of these infographics, they have a lot of content. Next slide, because I think I've animated this one, Yolanda. And you get this interesting mix of text and graphics. Sometimes the graphic actually expands on what's in the prose. So what part of Switzerland produces the wine? And that really requires a pretty deep understanding of that image. And sometimes the graphics use a visual metaphor that is broader than the specific prose, although sometimes that larger metaphor is spelled out. And you start to see these repeated images. And so you see this metaphor of the Swiss cheese model that certainly made the rounds in a lot of different forms that are similar but not exactly the same. And then next slide. And then recycled for things that are very different. And so I think as we think about multimedia, and this is really the message that I want to leave with, is that there's a lot of content here to try to understand, and a lot of combinations between the different types of language technology and understanding, and visual understanding of the data. That's all for me.
Great, thank you very much, Marjorie. Next up, we have Filip Ilievski, who is a computer scientist at ISI's Center on Knowledge Graphs, mainly investigating the role of background knowledge in AI reasoning.
Okay, thank you, Liz, and thank you, Yolanda, for organizing this. Next slide, please. All right, so when we think about, so given that this symposium is about, AI futures, I was thinking, what do we expect from AIs in the future? So when we think about AI in like 20, 30 years from now, we often imagine these scenarios where, AI typically embodied in like robots sort of coexist with us. So they are, on the top left, they are navigating sort of complex information. On the top right, we see robots coexisting with us in our household, so helping us with our tasks, cooking for us, cleaning for us, things like this. We think about robots that can self-drive, that can anticipate the behavior of other drivers. We think about robots that might even entertain us, given now that we haven't really seen a lot of live music, we're also starting to dream about robots, playing in our living room. Next slide, please. So we're thinking about all of these scenarios, and I think what is really at the core of all of them is that all of these agents that we foresee need to have the knowledge that we typically assume from people. And this knowledge is what we call common knowledge. So for example, if we consider the robots that are supposed to be in our, household, considering this like image here, we expect that they should know a few things to be able to perform these tasks. One is that they should know that cups typically contain liquid. So when you see these robots in the front here giving a cup to the child, we would expect that this cup is actually not empty, but it actually contains something. It also seems like on this picture, the cup is being sort of given in a careful way, which might indicate that the surface temperature might be too high. And we know as people that this is sort of something that we should be careful about, that people typically cannot hold very hot items for a long time. And the list goes on. These are just a few examples. And so why am I talking about this? The reason why common knowledge is very important is, as also pointed to Marjorie earlier, is that we tend to not mention in communication the things that are being obvious. So if you think about a recipe, for example, like this one here, the recipe ends with a statement serve. And now as people, we don't usually need further explanation because we know there's a soup and we know how soups are usually being served. We also know that typically the soup would be hot after it's being cooked, and that we should be careful and that should be placed in a bowl and so on. Unfortunately, if we look into the AI of today, we often see that the agents that we have out there typically tend to lack such common knowledge. And the main reason for this is the Grice maxim of quantity, which says that people generally are being informative but don't really state the obvious, which means that typically these agents don't have really the source to learn this from. So we have to think about other ways to communicate this sort of common knowledge to our agents. So the question is then, how do we actually build such agents that will have common knowledge in the next 20, 30 years? Next slide, please. So I think luckily we are not actually starting from scratch. So if we look in the history of the field of AI, there is a rich set of sources that people have been building. Traditionally, people have been generally building sources that have been in a manual way, like starting from Psych, and then Wikidata, ConceptNet, Atomic. A number of sources have been proposed for this. More recently, we have been looking into other ways to capture common knowledge in a more scalable way, using, for example, information extraction from a lot of documents on the web. And most recently, in the last 2 years or so, we have been trying to use language models or corpora for this purpose. And the interesting thing is that all of these strategies are sort of complementary to each other. So if we go for manual input, we get very high quality knowledge. It's a reliable knowledge. It's expressive. But then at the same time, this is an approach that's really hard to scale. It is also very expensive. On the other hand, using information extraction is a cheap and scalable solution, but typically yields lower quality and, again, incomplete knowledge. And finally, using language models or corpora give us the ultimate completeness and generalizability, but here we have problems with reliability of this knowledge and the expressivity. So what we have been doing in our own research is we've been trying to get a number of these different sources and try to integrate them into a single resource. Before my talk, Marjorie talked about getting this information from multimedia, from images. So we have integrated a number of these sources, including those coming from images, from lexical resources, and also from other more common sense sources of knowledge into a single knowledge graph. And we have been playing with this a little bit to see whether we can now take this knowledge that we have gathered and try to enrich the common agents that we have. Next slide, please. So one of the benefits of actually consolidating this knowledge into a single resource is that we can look into how to organize it into different dimensions and maybe look into how to axiomatize it. So in one of our papers this year, what we did is we took all the knowledge in our knowledge graph and we looked into ways to dissect it into different categories. The reason being that if we can do this, then we can actually look into ways to estimate how complete our knowledge is and what knowledge is actually still missing. So here on the right, you can see a table with the 13 sort of dimensions of common knowledge that we came up with, and examples for each of them about food. So you can see that we have information that's common, that's related much more to how people actually express things in language. This is sort of lexical things like foodie is derived from food. And then, we have things that are taxonomic, like food is a disposable product. We have part whole items like food, is being made of food ingredients. We talk about spatial knowledge, that food is often found on plates, or it causes desire to eat, so that would be motivational knowledge. So this is a way to deal with the kind of enormous and initially kind of untangible notion of common knowledge by first structuring it into dimensions and then studying what happens with each of these dimensions. Next slide, please. So the ultimate reason of why we actually do much of this consolidation of knowledge is to go back and actually feed these into these agents that I've been talking that actually lack it in the first place. And we have designed some methods to do this. So we have methods to combine these this common knowledge that we have gathered together with these dimensions with language models that are the state of the art of AI these days for many tasks, and to perform then reasoning across many of these tasks. So just to conclude, given this setup, I believe that one way to go towards achieving a comprehensive set of common knowledge, or at least capturing this common knowledge in future agents, is to follow this like three-step approach. First, we would gather the common knowledge that is available out there. We would consolidate it. Secondly, we need a way to organize it. Perhaps this would include ways to generalize and abstract over knowledge. And finally, we need a way to combine these with models that can reason over it. Thank you very much. That's the end.
Thank you so much. Thank you, Philip. So next we have Xiang Ren. So Xiang Ren is an assistant professor at USC Computer Science, and he is a research team leader at USC ISI.
Hi, hello everyone. This is Xiang. So I've been working on low resource learning and label efficient learning. So I've talked to many different practitioners, and in many conversations we found out that there's been a gap between like shifting these impressive results on academic benchmarks to really industry level kind of a pipeline. So I want to talk a little bit about that. Looking back, we've been seeing really surprisingly simple recipe for this modern NLP pipeline, which consists of these three parts like models, and then collecting label data and really just running on huge computing powers. And I feel like right nowadays, these model architectures and computing powers become more like a modality, commodity things that we can easily share and transfer across different tasks. For example, on the model, you can easily just like change a line of code on your Hugging Face code base, and then you can switch from one model architecture to the other. And the computing power is the same thing. You can switch to a larger GPU memory. But really, where does this label data coming from? Next slide, please. So just give you an example, I've been working a lot on information extraction and looking at this relation extraction task where you to find out the relationship between a pair of entities mentioned in a sentence. And there's been a lot of efforts on this task in past decades. For example, these TechRed data sets, which consists of 100,000 of label instances on 40 different relations, it's been a huge cost to create even just such a simple task for a simple task. For example, like every single instance on Amazon are gonna cost you $50, and this data set gonna cost you to $50,000 and take you more than a week to really create such a data set. Not to mention that nowadays we've been working on much more complex tasks like question answering that require multi-hop reasoning and co-reference and paraphrasing things. So next slide, please. But would just collecting more label data solve all of the problem we are encountering these days, especially building trustworthy AI systems? I don't think so. In one recent experiments or studies we just have by training a hate speech detection classifier using a bird over some social media data, we found out that because of the training data has some reporting biases where people talk when the sentence is mentioned in some social groups like Jews, those sentences tend to carry some hateful content or sentiment, and therefore those label data will more likely to be labeled as hate, and such that the bird just spuriously just captured that juries may be a very salient features for judging whether the content is hateful or not. And this got carried into the inference time when you really run this fine-tuned bird model over, let's say, New York Times articles. It turns out that more than 50% of the time, this model will think the New York Times articles is having hateful content, which in fact shouldn't be the case. So really, there's also the concern of can we build reliable and robust model by thinking about a different paradigm to really train the systems, just then feeding them labels. Next slide, please. So our kind of thoughts about this is really to go from just thinking human as a source of label to further talk to them and ask about the explanation why they labeled an instance in such a way. And this has been a very kind of a classical idea, which we'll call explanation-based learning, that was dated back to 80s, by Ray Moody and Tom Mitchell. But I think really the opportunity right now is we have all these modern NLP pipeline, neural network, and language models that are able to do better jobs in some smaller functions or operations like paraphrasing, co-reference, counting, logical operations. And can we rethink about whether we can take explanation that was solicited over one instance and try to generalize that explanations to many other examples that looks a little bit similar, right? For example, if you call something that is very nice, maybe in another sentence you call something extraordinary, where the explanation should also be able to apply. Next slide, please. So in order to do so, we need to really go from the previous strict matching kind of approach or framework, and to think about how we can go from hard matching to really some fuzzy matching and soft matching when we apply an explanation that was annotated for one specific instance to some other unlabeled instances. Next slide, please. So one effort we have been done in the past 2 years was this neural rule grounding for soft matching. So the whole framework is actually kind of straightforward. Think about if you have solicited a bunch of explanations from human experts or domain experts, and you can easily just do strict string matchings for those explanation or rules to a huge corpus, and you can get back a bunch of hard match instances. And that's what on the top right corner, which is the standard XY pairs. But then there's a lot of unmatched instances. That's where the opportunity sits. So we're trying to design a sort of neural matching process to apply this explanation to those unmatchable instances and creating pseudo-labeled data in the form of XY and then confidence score or matching score. And both this exact match data and this pseudo-label data will be used together to train a downstream model, for example, a relation classifier. Next slide, please. And this turns out to work pretty impressive in one experiment here where we not only just looking at the final performance of the system, but also looking at when you are given a specific amount of time to collect label data, which we call annotation time, how well you can build a system to achieve to a certain level of performance, right? In this case, the x-axis here is the annotation time ranging from 5 minutes to 40 minutes. And then the y-axis here is the F1 score of a relation extraction system. And then we have two different colors representing two kinds of ways of creating label data. The orange one is the traditional way where you just add a label to each sentence. And you can see that it's pretty much linearly grow when you spend more time, you will collect more label data. But then the system even trained with, let's say, 100-ish labels, which are solicited within 40 minutes of time, the system still perform pretty bad in terms of F1 score, which is like even below 5% F1 score. But then if you go from the explanation route and spend 40 minutes, you collect around a little bit less rules or explanation, but then the system you build with those explanations can go for between 40 to 45% F1 score. So that really give us the opportunity of rapidly build a system that can actually serve for some purpose, and then we can polish over that. So at the end, I think the vision I want to just share here is that ultimately we want to really turn the machine learning process into more of a conversation between the human experts and the machines or agents, where we can be having more flexible way to tell the system what you should learn and what you should unlearn, and to make sure that they are not spiral patterns or biases got easily introduced into this learning process. That's all I want to share. Thank you.
Thank you very much, Jon. All right, our last presenter is Ralph Wychettel. He is a research team leader at ISI. He has a long track record of research in natural language processing and its applications, including information extraction from text and speech, forecasting geopolitical issues, machine translation, question answering, and text generation. He is a fellow of the Association for Computational Linguistics.
Thank you, Liz. Next slide. So imagine a future where any question can be answered, even if the answer from the machine has to be, I don't know. Question answering has been looked at in artificial intelligence for several decades. The first round was providing English access to databases instead of, for instance, using SQL, or English access to knowledge bases and knowledge graphs, for instance, instead of using Sparkle. There was a second round where it was motivated mostly by information retrieval, where one would have a large collection of documents and need to find an answer to the question in that large collection of documents. What we're interested in is the long-term goal of being able to answer a question from any information on the web by synthesizing a succinct answer with a confidence in your answer and an explanation. Next slide. The most recent round of work in question answering has been stimulated by pre-trained language models such as BERT, Roberta, T5, GPT-2, etc. And here I'm just summarizing the state of the art in terms of tasks that have been performed and largely solved. So common sense reasoning is typically measured by multiple choice questions, and the example on the slide is physical reasoning. Another is reading comprehension, where one's provided with a paragraph and asked to answer the question based on the paragraph. Even as in the example here, the answer should be it's not answerable given the paragraph. This is typical, for instance, in elementary school, reading comprehension tests, or in tests for a foreign language speaker learning English. A third kind of task is competency in a subject matter. So think, for instance, the New York State Regents exams at the grade school level on science. Here again, multiple choice questions are the typical way of assessing what the machine knows. A fourth kind of question answering was provided by Google, where they had a question, one that was actually typed to Google, and a Wikipedia article, and the machine must provide a short answer given the Wikipedia article. Next slide. So that's the point of departure. I should point out that most of those kinds of tests that I've mentioned are in some sense viewed as solved in terms of research, because scores are reaching 85, 90, near or in some cases even above human performance. An assumption in all those examples is that you have hundreds or even thousands of correct questions and answer pairs for a machine to learn from. So our starting point is not that, but instead of, for instance, reading a paragraph, read a textbook, read a manual, and pass a test, as a human might be asked to pass a test to say that they have learned what's in the textbook, that they have learned what's in the manual. And again, trying to plow new ground, looking at the humanities and the social sciences as text material. So we've started this just in February, but we expect to release the task and a leaderboard in a few months. That will be machine processable versions of the text so that it's easy for people to participate in the challenge. Because of the prior work, we're not going to release any questions and correct answers. There'll be no training data. This will be a zero-shot learning task. We'll release a validation test set so one can test one's algorithms. And then from time to time, they can take the blind test set so one's not hill climbing on the test set. We'll provide an automatic score and baseline results. Our source for the textbooks is OpenStax, which has a Creative Commons license, therefore it's distributable. We've chosen 2, American Government with 17 chapters. There are questions that the authors wrote at the back of each chapter. We've converted a number of those into 400 manually derived true-false questions. True-false questions because they're very easy to score automatically. US History, 32 chapters, 560 manually derived true-false questions. Next. The baseline we're starting with is T5, which is available from Google, easily downloadable. It's been trained on 750 gigabytes of English text. The notion of training, I've given you an example in the middle of the slide. We don't need to go through those details today. But the important thing to know is that it's been demonstrated to be useful if fine-tuned for summarization or for machine translation or for question answering. Next slide. So even though we started in February, we have some baseline results to report. So using chapters 1 to 8 of the American government text as validation test. There are 186 true-false questions. Using T5, not the largest one, not the 11 billion parameter version, but the 3 billion parameter version, and fine-tuning with true-false or yes-no questions called Boschee. Random performance would be a score of 50% because it's a balanced test set. Taking T5, 3 billion out of the box, and depending on how we train it with Boschee, we get a score of 51 or 52. Now, a difference of 1 or 2 points basically is just a difference of 2 or 4 questions correct. So not noteworthy. However, if T5 has been retrained, right, open up the pre-training and read the book and then fine-tuned, we do get a gap to 56. And lastly, if it's an open book exam, where namely you don't have to read the book, cram all the information in and test without looking at the book again, you can do automatic information retrieval into the book. The score becomes 60. A comment about the scores, you shouldn't be, you could be discouraged about those scores. We are not, because the past examples I've shown you within a year, the test has largely been solved. In this case, we see that there's something that the system is learning. It can answer questions better than out of the box and better than random, but there's headroom. There's a basis for doing research. Next slide. So there are additional questions to be answered. One is we want to try baseline performance with other pre-trained language models, such as the 11 billion parameter version of T5, such as GPT-NEO, et cetera. For the open book exam, we want to carefully measure how much of the error is coming from information retrieval and how much of the error is coming from the question or the textbook was not correctly understood by the machine. We'd like to identify types of errors and categorize them. For instance, it could be the chain reasoning is a problem, or temporal reasoning, or any of a number of issues. And of course, suggest ways to improve reading comprehension. Now, ultimately, of course, we'd like to be able to decompose complex questions into their component parts and synthesize an answer. That might mean, in fact, running physical models or simulations. And now it's time for questions.
Great, thanks everyone. So if any of you listening in the audience have questions, please feel free to type them into the Q&A box. Meanwhile, I will get us started with a few questions I had as people were speaking. So going back to the first presentation, Jon, I was wondering if you could comment a little bit on what the experience is of using machine translation for low resource language. You talked about a lot of places where you guys are trying to deploy this in real world scenarios. You know, I'm pretty familiar with using Google Translate for something like Spanish, and it's pretty great, actually. And I was wondering if you could comment a little bit about the qualitative experience of where the state of the art is on these lower resource languages.
I would say it's highly variable, and it's not necessarily predictable by any metric that we've been able to nail down. So you might think that the volume of parallel data in terms of words is going to be predictive, but we haven't really found that to be the case. And you might also think that components such as like the morphological complexity, or maybe the regularity of spelling with data that's observed in the wild, if such a thing can be quantified, would be correlative, but we haven't. So there is definitely a correlation if you have as volumes of data grow, especially when you get orders of magnitude growth, you get better results. But we find that you can get anything from fairly coherent translations of all of the information to occasionally you'll get a word here or there. And there's definitely still work to be done. Now, the real impact of MT ultimately is usually not in just the plain text, but it's in the what you can do with that information in downstream applications. So in using the humanitarian assistance, disaster relief, sudden crisis as one example, getting a map showing the prevalence of people needing fresh water, for example, in one region of town is valuable information. And you can get this by small components of properly translated text, so water or fresh water needed or things like that, whereas the entire segment may not be intelligible, and you generally would want to have experts go, and if you really want to read the entire communication clearly, you do want to have experts, but this allows for effective triage.
Thanks. So another question I had as I was listening to people. So Xiang, I was looking at your explanations, and this is a very interesting way of really trying to get human knowledge to some extent into the system. A lot of the tasks that you were looking at and the explanations were relatively local within the sentence. And I was wondering, had you thought a little bit about broader explanations, or do you find that humans are better at looking at things in this much more narrow context?
Yeah, that's a great question. So we've been thinking a lot, as you've been thinking a lot about this. Like, I think the project start with, like you said, more local and what we said, what we call more grounded explanation, where all of the things was narrowed down to just looking at a specific sentence or paragraph, and then come up with any features that are exactly matching or grounding to some parts of the sentence or paragraph. So that things are more well-defined and more, let's say, structured. But then there's many times these NLP tasks require explanation that involve, for example, common sense that are not even talked about explicitly in the sentences. And those things, of course, for human, we can easily explain that out, and the other people that listen to this can also ground it because they have this kind of common ground and share knowledge. But this is really hard to easily, quickly implement it for the current NLP system, because the common sense representation by itself is an unsolved problem, and there's many people actively working on that. So I really think that we start these directions by trying to make something that are useful, at least for practitioner, to work on a small and narrower scope, and then hopefully in the next couple of years, we can really move this towards a broader scope. Yeah.
Thanks. Let's see. Maybe I'll ask a somewhat broader question really to any of you. So you've all spoke a lot about both the challenges and the promise of understanding language, or the understanding that is behind language. I was wondering if any of you had any thoughts on, this is highly speculative, but what is the next big jump going to be? Is there something you see that's currently a challenge for the systems in front of you that you actually think, yeah, maybe 5 years from now, we'll have actually solved this problem? I mean, Ralph, you were saying, for instance, we're not worried about this task because it seems like we're solving problems like that. So is there anything in any of your fields that you look at and think, yeah, this is it's really challenging, but it's kind of ripe for the picking and might be something that could be coming up?
Well, let me answer your question indirectly, right? I think making these predictions is extremely unreliable. So I remember 4 years ago being skeptical about deep neural nets. The way I would express that skepticism was, they've proven you can do sequence to sequence tasks really well. So part of speech labeling, parsing, et cetera. What would really convince me that there's something there was if they could predict structured knowledge. And within a year of my saying that, the paper by Luke Zettelmeyer and others at the University of Washington and AI2 came out saying you could do coreference more accurately than ever before. So that was a turning point for me. So at the same time, I'm not willing to make a 5-year prediction, which I'm sure I will be wrong about.
I think go ahead, Phil.
Right. So I feel like one of the things that I see that we are making quite a big progress, and I consider it to be a big uh, um, sort of downside of AI these days is the generalizability to unseen scenarios. I don't really think that this will be fully solved in 5 years. I think it's a very lofty problem with a lot of different it's the long tail is very diverse and very rich. So I think there are a lot of different phenomena there. But I think that also I think one of the speakers was talking about zero shot evaluation. I think this would be one thing that we would be making much more progress, and I think we already are with all the big language models coming up these days and the integration with background knowledge. I would say that this would be one thing that will get much closer to solving, or at least I'm hoping.
I think some more kind of pragmatic tasks like understanding opinions and understanding, kind of latent meaning. There are components of this that really shade into common sense reasoning, and I think will continue to be vexing. And there's also quite a lot of ingenuity that we can use to express these things. But it still seems like the kind of fine-grained what you mean despite what you say aspect could I expect that we'll see tasks in that direction. I don't know that those will actually show that we've managed to capture pragmatics identification, but I do think that we'll be looking for more subtextual analysis.
So yeah, I won't be saying any like particular tools or application that can really be achieving human performance. But I think one thing I really see in the progress is the evaluations in the research community. I think in the next couple of years, people won't be only looking at, let's say, a single number or a couple numbers of metrics over these fixed text sets. They will be looking at a broader set of behavioral measurements of the system, maybe a measurement of the label efficiency, maybe the measurement of the robustness, the biases. They will be considering multiple test sets for testing one systems, and then to draw a conclusion, then just looking at reporting some 2 or 3 data sets. I think that's probably the trend gonna happen within 5 years, and then that will change a lot of the research behaviors of the community, and also maybe making us closer to transfer our technologies to the practitioner as well. Yeah.
Right. Great. Well, I think that is all I have. I think we only have 2 minutes left. So I'd like to thank all of our speakers today. Thank you so much for really interesting and diverse look into the world of language in artificial intelligence. Thank you.
Thank you very much, Liz and Ralph, Jon, Filip, Xiang, and Marjorie. This was a great session. I think you're really increasing our hope that AI systems will be more and more knowledgeable about the world, about ourselves, about how we express our thoughts and communicate with AI systems better and make them more informed about any decisions that they make. Thank you. Tomorrow morning, we will resume at 9 a.m. Pacific time. We have a session on decision making, speaking of AI systems making better decisions. And then it will be followed by a panel discussion and an invited talk on healthcare and biomedical applications of AI and data science. We look forward to seeing you there tomorrow. And thanks everybody again for making time to join us today.